All right, welcome today to the senior physics video introducing inelastic collisions. You should be taking notes during this time, so make sure that you have your journal at the ready. The idea is that you're able to pause this video to copy down, go back, rewatch sections to make sure that you get a full understanding of all of these examples. We're going to have a quiz when we come into next class, a do now quiz on some of these topics, so make sure that you understand the example problems that we see here today. We have some easy objectives and one sort of more complicated example problem that we're going to look at. We have three things that we want to learn today. First, we want to be able to distinguish between elastic and inelastic collisions. It's a very easy objective. Then we want to be able to identify the total momentum before and after a collision. Also easy. A more complicated example, and here it says 2, so let's change that right now. So where it says example 3, students will be able to solve for the final velocities resulting from an inelastic collision. Those are going to be our example problems today. They're not that bad, but you definitely want to pause, stop, take a look at those problems so that you're ready for next class. Okay, let's get started. First, we're going to talk about collisions types. The first type of collision is an elastic collision. When you think of elastic, you should be thinking of springs. If you think back to our energy unit, elastic collisions are bouncy, just like springs are. And so if two objects, when they collide, if they bounce off of each other, that would be a partly elastic collision. Think of something like a super ball, or the classic example for elastic collisions are billiards or pool balls, like we see right here. When you hit the cue into the pool ball, a numbered ball, it bounces off in a nearly perfectly elastic collision, and so we'll be seeing lots of examples this unit with that, particularly when we look at two-dimensional collisions. The next type of example, and mostly what we're going to talk about today, again, my numbering is off, I'm sorry about that. Here, number 2, we've got inelastic collisions. These are easier problems to work. Inelastic collisions are when any two objects collide and they stick together. Think of dropping a piece of clay on the ground, or even you can approximate this for like a water balloon collision with somebody. Even though it dissolves, its momentum is transferred. It sticks to the other object. A classic example for inelastic collisions are car crashes. If you have car crashes at high velocity in particular, the two cars tend to stick together. This picture is a particularly tragic example, not because I think anyone got hurt, it's just that is a very expensive car. So you definitely want to make sure that you get this next section of notes down clearly. It's momentum conservation. It's the main idea of this unit, and we're going to be using it for basically all of the problems that we see here. And so here we go. The total momentum of objects before they collide is always the same as the total momentum of objects after a collision. So to say that in another way, if we have two objects, A and B, if we found each of their momentums before they collided and added them together, then they collided, and we looked at each of their momentums after the collision and added them together, those two sums should be the same. If that didn't make any sense, don't worry about it. We're going to look at some examples right now that's going to make it very, very clear. So the first example we're going to look at is an example sort of in a train yard where we have trains that are coupling together. And so what we want to imagine is that we're trying to assemble a large line of trains. So we're going to see these two train cars coming together. The first train car here on the left has a mass of 4,000 kilograms. The second train car on the right has a mass of 2,700 kilograms. Now we're going to add to this idea by saying that this first train car is coming in with a velocity equal to 5 meters per second. And the second train car on the right, we're going to say has no velocity at all, 0 meters per second. So the first train car, which I'm going to show in red, will collide with the train car on the right, and then they will both move off together in the direction to the right. And we're trying to figure out what that velocity is going to be after they collide. So how do we do this? It's a good question. We have to use our idea of momentum conservation. Again, this is an inelastic collision. Should make the problem fairly easy. but we can use it for both elastic and inelastic collisions. We're going to use this idea. So momentum conservation says that the total momentum we find before the collision should be equal to the total momentum we find after the collision. So let's do that. And so what I'm going to write down is I'm going to write down momentum of object A before the collision plus the momentum of object B before the collision, B being the object that isn't moving, should be equal to the momentum of both objects together after they collide. Now, since this is an inelastic collision and they stick together, we can treat these as one object. Okay? I'm going to put a prime notation on here. If you see it right there, that prime. That does not mean derivative. Prime simply means after the collision, and so you'll see that as we work through problems in this unit. So let's take it through the next step. The next step in this should be writing the momentum equation. So MA VA plus MB VB it's going to be equal to the momentum of both objects when they come together. Now, the momentum of this object is the sum of both of their masses, because they've stuck together, times v prime, the velocity after the collision. This v prime right here is what we're looking to solve for. So, let's see what we have. Do we have mass for object A? Of course, I've now switched my notation, I noticed, to 1 and 2. That's fine. This is going to be 4,000 times 5. Now, since object B, or object 2, isn't moving, that momentum ends up being 0. And then if we look over here, we have to add their masses together. That's going to be 6,700 kilograms times v prime. After this, it's just algebra. You can work that through on their own, but we end up with a velocity after they collide that's equal to approximately 2.99 meters per second. So once these train cars come together, they move off in this direction at 2.99 meters per second. Notice that this is slower than the 5 meters per second that the lighter train car came in with. That's because since the mass increased by adding object 2 or object B, the velocity has to decrease in order to keep the total momentum the same as it was before the collision. The total momentum before the collision has to equal the total momentum after the collision. Let's look at one more example. A 75-kilogram astronaut is accidentally cut loose from the space station. In order to get back, he throws his oxygen tank away from himself with a velocity of 10 meters per second. If he then moves away with a speed of negative 1.4 meters per second, what was the mass of the tank? Again, that was really fast, so I would take a moment, pause this video, read through that again, and then come back. All right. So what we're going to see here is that this astronaut is not moving. He's stationary in outer space, and he is stuck. There is no way for him to get back to the space station. So what he's going to do is he's going to take his air tank, and if you look here, he's going to throw it away from himself. Let's watch that again. Throw it away from himself with a velocity of 10 meters per second. So what we want to do is we want to figure out how fast or how much mass did that tank have. So let's think about before the collision. We have astronaut and air tank. So momentum of the astronaut plus the momentum of the air tank, we'll call that B. That should be equal to the momentum of both of those objects after they break apart. So here we have PA prime plus PB prime. Notice the prime notation for after the collision. Now, you should be asking the question, collision, I don't remember seeing a collision here. Well, this is like a collision run in reverse. If you think about it, the objects are stuck together in the beginning and then they break apart at the end. It is like a collision run in reverse, but we can still use momentum to analyze this situation. So since nothing is moving at the beginning, we know that the total momentum before the collision has to be equal to 0. So PA plus PB at the beginning, right here, in this situation the velocity is 0 for both of those. So we know that the total momentum here is 0. Ha. We know that the total momentum here is 0. Excellent. So as we look over to the right side, we also know that the momentum of the astronaut is going to be 75 kilograms times negative 1.4 meters per second. And then the air tank we know is going to move to the right with a velocity of 10 meters per second, but we don't know the mass. Using this equation, you see that the only thing that we do not have is the mass of the air tank. You can do some algebra, and once you get down to it, we find that the unknown mass of the air tank, mass of object B, is equal to 10.5 kilograms. Now, one thing I want you to notice is that I don't ever use prime notation when it comes to masses. That's because before the collision, after the collision, the mass is never going to change for the individual objects, so there's no need to use a prime notation to indicate before or after a collision. However, with velocities, they do change before and after a collision, so I will use a prime notation for velocities. All right. Take a minute, rewatch this problem, see if you have any questions, and then come ready next class with them. One last thing that we're going to look at is we've got the problem of a frozen lake. This is a classic momentum problem. Imagine that you are in the center of a frozen lake, but I do want you to imagine also that this lake is totally frictionless. The temperature is dropping, and it doesn't look like you're wearing much clothing in this picture. So you got a problem. You need to get to the side of the lake somewhere, and that side is either going to be somewhere over here, or somewhere up here, somewhere down here. Anywhere that you try to go, the problem is since it's frictionless, you don't have the ability to walk in that direction. You have nothing to push off of. Even if you fall, you're going to be stuck. And so the question that I'm going to pose to you is, how are you going to get to the side of the lake before you freeze to death? There definitely is a way to do it, but you can't try to walk. That's definitely not going to work, and you can't fall down. That's not going to work either. So take some time to think about that. We'll bring it up next class for sure. In the meantime, pause, rewatch some of these parts, think about it, and come ready to take a more complicated Do Now quiz on some of these ideas next class. If you watch this video and understand it, you should be doing fine. Thanks for watching, and we'll see you.